Okay, so consider an AR2 model xt minus 0.9 xt minus 1 plus 0.1 xt minus 2 equals a sub t. Let's just say gamma naught is 2. And what we want to do here is find an expression for rho k. How do we go about doing this? So we have an expression for rho k in terms of the roots of the characteristic polynomial, so the starting point has to be the characteristic polynomial. So we have xt minus 0.9 xt minus 1 plus 0.1 xt minus 2 equals at. We can rewrite xt minus 1 as b times xt and xt minus 2 as b squared times xt equals at. Xt is in common, so 1 minus 0.9b plus 0.1 b squared by 80. So the characteristic polynomial is 1 minus 0.9b plus 0.1b squared. And we can set that equal to 0 because we're solving for the roots. So that would be phi b and things to note here, the roots of the characteristic polynomial must lie outside the unit circle, and the coefficients are inverses of the roots. So I have to make a change here. The coefficients are not inverses of the roots directly, they are functions of the inverses of the roots. So that said, let's find the roots of this characteristic polynomial, then we could find a general form for rho k. So the characteristic polynomial is 1 minus 0.9b plus 0.1b squared equals 0. We want to find the roots, so we'll just find the roots here. B is minus b. I'm going to use the quadratic formula. A here is 0.1, b is negative 0.9, and c is 1. So the roots are minus b plus or minus square root of b squared minus 4ac divided by 2a. So minus of minus 0.9 plus or minus square root of 0.9 squared minus 4 times a times c, which is 1. By 2 times 0.1. So we will have 0.9 plus or minus square root of 0.81 0.2 and that would give us 1.54 over 0.2 and 0.9 minus 0.64, which is 0.26 over 0.2. So I get 7.7 and 1.3. So the root of the characteristic polynomial are R1 equals 7.7 and R2 equals 1.3. Note, both R1 and R2 lie outside the unit circle. This would imply the series is causal and stationary. You may recall that stationarity and causality are important conditions that we need in a time series if we want it to be autoregressive. So it is guaranteed, a series is guaranteed to be causal and stationary if the roots lie outside the unit circle. So now that we have the roots, V would be 2, M1 is 1, and M2 is 1. We went over V, M1, M2 in the previous video. M1, M2 are the multiplicities of the root. And we have two distinct ones. R1 is 7.7 and R2 is 1.3. And we have our expression for rho k, and rho k is sum I equals 1 to V, sum j equals 0 to mi minus 1, Cij, k raised j, and r I raised negative k. So V is 2, so we will have I equals 1 to 2, j equals 0 to mi minus 1, Cij, k raised j, ri raised negative k. So when I is 1, we'd end up getting sum j equals 0 to m1 minus 1, c1j, k raised j, r I is 1 minus k. And when I is 2, we would have j equals 0 to m2 minus 1, c2j, k raised j, and r2 raised negative k. And m1 is 1 and m2 is 1, so we have 0 to 0, c1j, k raised j, r1 raised negative k, j equals 0, m2 is 1, 1 minus 1 would be 0, c2j, k raised j, r2 raised negative k. And plugging in j, we have c1 0, k raised 0, r1 raised negative k, c2 0, k raised 0, r2 raised negative k, which would simply give us c1 0, r1 raised negative k, c2 0, r2 raised negative k. And we have the values of R1 and R2. R1 is 7.7 and R2 is 1.3. Raise k. So that is our expression for row k. But if we have to find the constants c1 0 and c2 0, we will need to find, or we need to have, the autocorrelation functions. Since this is an AR2 model, we can make use of the first two autocorrelations to find an expression for row k. How do we go about doing this? Well, we know that row 1 is phi1 plus row 1 phi2, and row 2 is row 1 phi1 plus phi2. And these are the standard Ewell-Walker equations. And we have the values of phi1 and phi2. And in our question, phi1 was negative 0.9 and phi2 was 0.1. So this would imply row 1 would equal phi1 negative 0.9 plus row 1 times phi2, which is 0.1. We'll have row 1 minus 0.1 row 1 would equal to negative 0.9, and row 1 times 0.9 would equal negative 0.9. Row 1 ends up being negative 1. And row 2, on the other hand, is negative 1 times phi1, which is negative 0.9. Phi2 is 0.1. And row 2 would simply end up being 1. So we have the values of row 1 and row 2, and since we have the values of row 1 and row 2, we can actually find the coefficients C10 and C20. So going back to row K, so let K equals 1 or equal 1. This would imply row 1 equals C10, 7.7 raised negative 1 plus C20, 1.3 raised negative 1. And row 1 happens to be negative 1, so negative 1 would equal C10, and 7.7 raised negative 1 is 0.1. 1298. Likewise, 1.3 raised negative 1 is 0.7692. I'll round it to 2 decimal places, so C10 times 0.13, C20 times 0.77 would equal -1. And likewise, if we let k equals 2, row 2 would equal C10, 7.7 raised negative 2, plus C20, 1.3 raised negative 2. So 1 would equal C10 times 0.017, C20, 1.3 raised negative 2, 0.591. So we can only go up to 2 autocorrelations to determine the constants because this is an AR2 model. If this were to be an AR3 model, we could go with k equals 1, k equals 2, k equals 3, and use those values to find the coefficients or the constants C10 and C20. So now we end up having 2 equations, that is equation 1, that is equation 2. Let's bring them together. And this looks very much like a matrix. So what we have here is negative 1, 1 equals 0.13, 0.77, 0.017, and 0.591. And the 2 constants are C10 and C20. Now, we will need a TI-84 calculator to find the constants C10 and C20. You have to define 2 matrices, one for the right-hand side, the 2 by 2 matrix. The other is for the vector on the left-hand side, which is negative 1 and 1. And very similar to our previous estimation, where we estimated coefficients, we could call this matrix W, and that U, and this is C. So this would simply mean C is U inverse multiplied by W. So you can use a calculator, so Google or look at YouTube on how to find the inverse of a matrix using TI-84. And if you use the inverse of the matrix U and the vector W, so W is right here, U is right there, we will find the coefficients to be negative 21.35 and 2.306. So that would imply C10 is negative 21.35 and C20 is 2.31. So therefore, row K is negative 21.35 times 7.7 raised negative K plus 2.31 multiplied by 1.3 raise negative K. So now that we have a general expression for row K, we can pretty much find any autocorrelation value for changing values of k. For instance, if we plug in k equals 3, we could find row 3. If k equals 4, we could find row 4, and so forth.